Hi, I'm Robert Crowe. I'm going to be talking about TFX, TensorFlow Extended, and with me is Gus Katsiapis, who is the Uber TL of TFX. So he's going to be around. We're going to be answering questions and meeting with you. So let's go ahead and do the talk, and then we can follow up after. So inside Google, there is this thing that we call TFX, or TensorFlow Extended. And there's all these pieces to it. And a couple of years ago, we made the decision to make this available not just inside Google, but outside of Google as well. And so now we have TensorFlow open source. And many of the pieces of, I'm sorry, not TensorFlow open source, TFX open source. And now many of the pieces of TFX that have migrated from internal to external are available now. These are the pieces, if you look at the, I want to call that color blue. Those are the pieces that are available today for you to use, and many of you probably are. Actually, let's see a show of hands. Who here has worked with any part of TensorFlow open source TFX? Maybe half, maybe a third. Can't really see upstairs, the lights are too bright. Good. And let's do another one. How many, who works with TensorFlow at all? Okay, that's most of the crowd. Good, but not everybody, because not everybody does using Beam. There's other things you do besides TensorFlow or machine learning or what have you. So those are the pieces that are available today, and the ones in white are pieces that we will be filling in as we go forward. TFX within Google has been incredibly important. So it's important not just within Google, but within several of the other, what we call alphabets, or other parts of Alphabet. And major products that you're all familiar with currently using TFX. So inside of Google, TFX and the TFX project has been a huge success. It was not the first of the machine learning pipelines that Google had. It has evolved over time because we've learned things along the way and made improvements. TFX is the latest and greatest, and most of the, or at least a substantial portion of the ML within Google is done using TFX, as well as some of our partners, including Twitter. And you'll see Twitter says some very nice things here about TensorFlow. They're actually migrating from a torch-based environment, where they have done the migration, and went out and evaluated what was available, including PyTorch. And they made the decision that TFX and the TensorFlow ecosystem was a good match for them. And throughout the presentation, you'll see some QR codes. Those are just pointing to the URLs for the relevant documents that are mentioned in the slides here. So it's important not just within Google, but within major partners and throughout the ML community. We hope to see increasing adoption. So what are the challenges when you move from maybe ML research into production environments with machine learning? What are the challenges that you run into? I think within this audience, many of you are probably familiar with a lot of the issues that you will run into, but let's talk about them. First of all, you have all the problems that you have with any machine learning development. Things like labeled data, the ML6 talk that we just had. Labeled data was an important part of making that work, and it's not easy to collect that labeled data, and especially good labeled data. It's feature space coverage, making sure your features actually cover your loss space. That's difficult in a lot of cases. Minimizing your dimensionality, getting the maximum predictive value from the data that you have, maybe figuring out what sort of feature engineering will give you that. Things like fairness are increasingly important. You want to make sure that your solution is not unfairly biasing different parts of your customer base or your community. Rare conditions. You may have conditions, especially in things like healthcare, that occur very infrequently but are very important. And when you're developing a machine learning solution, trying to account for those and make sure you serve them well is difficult. And finally, data lifecycle management. You'll notice in all of these cases, we're talking primarily about data. Data is a first-class citizen in any production machine learning system. You need to think about data in the same way and with many of the rigorous methodologies that you currently use for production code in any production deployment. So it's important that you include data in your thinking when you're designing a solution. But you also have all the issues that you have with any production software deployment. And I think I'm probably preaching to the choir here. You guys are probably very familiar with all these issues and really the standard methodologies for dealing with them. But things like scalability, which will largely be driven by your data, both the size of your training data set and the rate at which you may be taking in data for inference, extensibility, configuration, you just go down the list. Testability. Testability can be challenging in ML environments. So you have all these things to deal with, and we at Google had all these things to deal with when we embarked on doing machine learning. So that's what TensorFlow Extended is all about. There's a great paper here. It was actually done back in 2015, but it's still extremely relevant. And it talks about the hidden technical debt in machine learning systems. I highly recommend it. The QR code points to it. The bit.ly link points to it. Great paper. So the role of Apache Beam in TFX is extremely important. Really, without Beam, we wouldn't have an open source TFX. So first of all, Beam gives TFX a unified batch and stream distributed processing API, because distributed processing is extremely important to the kinds of things you need to do in a production, scalable, really petabyte scalable system. You're going to need a distributed framework. Beam gives us that. Currently, we're using the batch side of things, and at some point, we'll be moving to streaming as well. The set of SDK front ends is very important. We're using Python currently, but having those others available is important as well. And the set of runners that are available, including the local runner, which, as you guys know, is very, very nice for doing development. But Flink and Spark, when we go out to developers who are going to adopt TFX, we want to make sure that we don't impose our choices on them. We want to be as flexible as possible. So if they already have a Flink deployment, we don't want to force them to use something else. We want to allow them to adopt TFX and use whatever platform and infrastructure they currently have, including Google Cloud Dataflow. So if you look at the different parts of TFX, there's a couple of different layers, but several of the component stacks here are powered by Beam. On the left here, when we're ingesting data, the ExecutOrs component is using Beam. When you get to generating statistics for your data set and figuring out a schema, trying to infer a schema, again, we're using Beam. When we're doing transformations to do feature engineering, again, using Beam. So you can see how important Beam is within TFX, as well as for doing model analysis. Actually, let me go back to that slide real quick here. One part I forgot to mention was the layering with libraries. So you'll see the boxes in orange. Those are libraries, and they're available as separate modules that you can use for whatever needs you have. In this case, they're being used to implement the components below, the boxes in blue and, well, the boxes below the orange row of boxes. Those are components. We'll talk a lot about components in a bit. In fact, right now. So, a TFX pipeline is a directed acyclic graph, or DAG, and it is made up of components. Those components are structured like this. So there's really three main pieces to a component. a driver, an executor, and a publisher. A driver goes out and looks at the environment in which it operates and decides, should I or should I not run this component? And if it decides that it should, then it's going to supply the necessary input to the executor. The executor is where the work is done. So whatever you happen to be doing in that component, that's where it happens. That's where you would write your user code in most cases. And the publisher takes the results from the executor and it puts it back into something we haven't talked about yet, the ML metadata store. Don't worry, we'll get to that in a second. You need a configuration for each component, and that configuration is written in Python. And in a lot of cases, it's like 1 or 2 lines. So configuration is important, and it's very flexible, and really pretty easy. The metadata store is a key component that we're going to get into in a little bit, but what I want you to take away from this is that the component is taking input, including the state of the environment, from the metadata store. It's doing something inside, and then it's writing the result back into the metadata store. And that's how components communicate. So one component writes in something, another component reads it out. That's how things flow through the DAG, through the pipeline. So let's talk about pipeline styles for a second, because there's a particular style that we've chosen, and I think it's good to understand why. You could, and this is perfectly valid, you could just do a task-aware pipeline, where you simply run one task, you wait for it to finish. When it finishes, you kick off the next task in the sequence. That's fine, works, but if you do more, you get a lot of benefits. So we do task and data-aware pipelines, and really, fundamentally, it's mostly data-aware. So what we're doing is we're taking data in, we store it in a metadata store as artifacts, and we run our components based on the state of the data in the metadata store. So it's aware, the metadata store becomes the environment in which the component lives. So metadata, it turns out, is a very important part of making TFX, and I would suggest probably any ML production pipeline system work. So what is it? What goes into it? Well, there's artifacts. And artifacts are things like trained models or data sets in various stages of transformation, including splitting, or things like metrics when you've done calculations on the results, not just at the top level, but of individual slices within your data set. All those create the environment, the data environment that the pipeline lives in, as well as execution records. So every time I run through the pipeline, that becomes an execution, and keeping a record of those is important. And here's where we start to think about the lifetime of a pipeline, including the lifetime of the data in the pipeline, but typically a pipeline won't just run once, it'll run today and tomorrow, or maybe an hour from now. It'll run continuously over the life of that ML solution, and it will evolve as that happens, because your data evolves, and your model, in many cases, will need to evolve along with it. Managing that requires that you have things like execution records available. And being able to understand the flow through your DAG of the different artifacts is important. So if you want to trace back, for example, you have a model and maybe it's not training today as well as it did yesterday, well, why is it doing that? In order to understand that, you probably want to be able to trace back and find out, well, what changed about the data? Well, to find out what changed about the data, you need to be able to find out what data was it trained on. You can only do that if you have the lineage or provenance of all of the artifacts in your metadata. So, finding out which data a model was trained on, it's a key benefit of having a data-aware pipeline. Being able to compare previous model runs. So again, you have a model that is behaving differently today than it did yesterday, but really understanding how it's behaving differently. This is giving an example where I'm comparing two different models in TensorBoard. Carryover state. So if I've spent, say 3 days training a model over a couple of terabytes of data, and I've only run it for, let's say, 100,000 epochs, but it looks, from what I'm seeing in the metrics, like I should run it for, maybe another 100,000. I don't want to start over. I want a warm start. So being able to have the carryover state allows you to do that. And then previously computed outputs from each of your components. Again, we're looking at large data sets here. So it may be the case that it takes hours to run a component. If I'm going to rerun that pipeline and the input to that component has not changed, then I don't want to rerun that component. I just want to pull the known result from cache. So this is the kind of thing that you get when you can query metadata. You can pull out what's going on with your training runs and the attributes and artifacts that your pipeline's created, including lineage. So being able to trace back through the different components of your pipeline to find out what was connected to what and where was it. And then looking at it from the other direction, I've trained the model. Now I want to look back at the data and see how do the different features match up against the distributions that were there. So being able to do the analysis, and keep in mind this is looking at a particular model. So I'm not saying look at this data and tell me what, give me a histogram for this data. I'm saying for this model, tell me what the characteristics of the data were. Including slicing. So slicing is important. I don't get into slicing too much here, but the key takeaway for slicing or any sort of deep analysis of your performance metrics is to understand that for each individual inference request, each individual user, they have one data point that is going to be their whole experience of your model. So your top line metrics may look great, but if you have big holes in your performance across different slices of your data, you're going to have significant numbers of users who are going to have a poor experience. So understanding that is important, and it can be financially important. You can use TensorBoard. One of the things that TFX does is to save the data for TensorBoard to use. So when you're running your trainer, you can analyze the results in the way you would normally if you're just training in a notebook or something. And you can compare multiple model training runs. Those could be the last two, or they might be comparing this month with last month. And you can compare different data sets. So again, we're looking at model IDs here. So I've got a model that I trained today, and then I want to compare it to the one for last week. But what I really want to see is how is the data different? So this kind of visualization, which is really empowered by having that metadata, gives me the ability to do that at the model level. I don't have to go find that data set and do it manually. I can make that query based on the model. Okay, remember we talked about there are three major parts of a component. There's a driver, executor, and a publisher. Executors are important to developers because that's where, in most cases, your code is going to live. So let's try to understand executors a little bit. You have executors like Transform that run on Beam. And some of you may have heard of Beam, I think. So, you know, it does great stuff, and that's great. Then you have, oh, so here's an example of what that looks like. You guys have probably seen this syntax a million times. So that's an executor. That's actually the StatsGen executor. So, but it's also using Beam. Then you have, well, I think one component type, a trainer, that really is just using TensorFlow. So that's, when you think about starting the ML journey, usually you think about modeling. That's what most people have gone to school and learned about when they learn about machine learning and data science. And it's really when you get into production systems that you learn about all the rest of this stuff. But TensorFlow is what people will be familiar with when they're coming in usually. And then you have some executors that are really just doing stuff that you can do in Python. So Pusher, for example, which pushes your trained model into your deployment targets, that's just written in Python. To do this, you need orchestration. You guys know that. And we try to be flexible about what sort of orchestration you can use with TFX. So it's really extensible. Currently, we support 2, Apache Airflow and Kubeflow. That's just showing the same DAG, the same pipeline in both. And when you put it all together, this is sort of the canonical DAG topology that you would see. So on the left, you're ingesting your data. You pass through pre-processing and statistics generation and inferring a schema. You do feature generation in your trainer, in transform, and then pass the results of that to trainer. We're going to talk a little bit more about the details around that. And then you're going to do model evaluation to evaluate the performance of your model, including at a deep level, looking at individual slices. And then you have to make the decision. Is the model that I just trained better or worse than the model that I currently have in production? And to do that, you need to define what the criteria will be. And if it's better, then you want to push it. And you can push it to several different deployment targets here. So you could be pushing it to Hub or TensorFlow.js for a JavaScript environment, TensorFlow Lite for a native mobile application, TensorFlow Serving for servers or server farms, or all of the above. Here's what a pipeline definition, or really this is the definition of a DAG, looks like. So that's, you can see the one that's highlighted there is transform, but those are all components. So it's really, when you write a DAG, it's really not that much code, maybe 50 lines of code. So let's dig a little deeper into the individual components. And we're going to start with the beginnings of the pipeline where we're doing data ingestion and the data analysis. This is using, well, it's using Beam. It's also using the TensorFlow data validation library. So ExampleGen is taking in raw data in a number of forms, and you as well can create your own custom ExampleGen in this case, and then it's doing a split and creating TF examples. Using Beam to do that, and that's, those 2 lines, that's the whole configuration. Then we move into data validation and analysis. So StatsGen. StatsGen is really looking at it's doing a full pass, one full epoch over your training data set, and it's calculating statistics. And that's when you're beginning the ML development process, understanding your data is the most important thing you can do. So this gives you tools to help you do that. And remember, we're talking about large data sets, so these are often way beyond what you could reasonably do in a notebook with pandas or something like that. But we give you the visualization tools available to look at things like your histograms for each of your features and the different descriptive statistics. Again, leveraging the power of Beam. So that's the kind of thing that you get. You get individual feature statistics and the histograms for those, and you can slice those. There's control over trying to do different looks at that data. SchemaGen. So SchemaGen is also going to do a full pass over your data and try to infer the types of each of your features, including things like, if I have a categorical feature, what are the valid categories that are acceptable? So it's going to make a pass over that, the end result of that going into metadata as a schema, and you get the output of what it has inferred. Now, it's important when you're doing this that you don't just take that and run with it. You need to really take a look at that schema and think about what it's given you and make sure, based on your domain knowledge, that it is what you need. So for example, if it's missing categories that you know you're going to see, maybe they weren't included in your training set, but you know they're out there, you need to make sure that those are included. Otherwise, you're going to throw anomalies. Data validator. So data validator is taking the result from StatisticsGen and SchemaGen and doing the validation on your data. So what it's looking for are things like missing values, values that are the wrong types, things like categorical variables that have values that are not expected. Transform. Transform is one of the more complex components. It's taking the results from example gen, so that's your input data. It's taking the schema that we just talked about and some code. And the code can tend to be more complex than the other components because it's doing more. That's where you're doing your feature engineering. And it's using Beam to do that as well as TensorFlow. So it can be more complex, and it's going to output two things: a transform graph that will be included in your final saved model as the input stage of your model, and the transform data itself. So really what's happening here is it's making a pass over your data and doing your transformations, and it's going to output two different kinds of things. TensorFlow constants for things that are the same for all of your data points, like the standard deviation of that particular feature for your data set. And TensorFlow ops for things that change from example to example. Those build a graph that then gets included in the final saved graph after you trained your model. And the reason that's important is that becomes part of what you deploy, and you're using exactly the same transformation both in training and in inference. So you don't have this problem, which you often have, of different code that's trying to do the same thing in two different environments. If you're trying to do feature engineering in your training environment and that's running on Python, and your inference system is running on Java, and you're trying to make sure that your code is doing the same thing in both places, well, hopefully it is. But let's just eliminate the possibility that it's not and include a transform graph in the saved model. So that's what that's doing in both training and serving. Finally, we have trainer. For anyone working with TensorFlow, training a model is pretty familiar, and that's exactly what trainer is. So it's taking a TensorFlow model, it's training it, it's taking the results of your transform that we just talked about, including the schema, and it's going to output really two different kinds of things: an eval saved model and a saved model. The eval saved model is just a saved model with some extra stuff that we're going to use for evaluation. I have 10 minutes. The configuration for a trainer is about what you'd expect. It's things like the number of steps and so forth. And you can use TensorBoard with it. And in this stage of the development process, TensorBoard is really powerful and fun to use, really, including comparing different training runs. So maybe you made a change, maybe you adjusted a hyperparameter, comparing the difference. So then we get into model analysis and validation. An evaluator is where we're going to do that model analysis, and that's using the TensorFlow model analysis, TFMA, library, which is also available separately. So it's taking in example gen, your original data, and the results from trainer, And it's really doing what you tell it to do, because you do have to go define what slices that you want to look at. But it's giving you the tools, including the visualization tools, to do that. So it's important for you to really dig into your data and understand different parts of your data, and this is where the domain knowledge becomes important, right? Which slices are going to be important. So if I'm trying to predict things around a hospital, times of day might be very important to the outcomes that I can expect. I might get a very different outcome at 8 in the morning than I do at 3 a.m. So understanding those different slices becomes really important. Once I've done that, I've kind of at a place where I've done my training and I understand the results, and I want my pipeline to decide, is it time to push that model? And that's what Model Validator does. You have to tell it what the criteria will be. Once you do that, then it's going to take that model, compare it to what's currently in production, and make that decision. Should I or should I not push it to production? And when it pushes it, it's going to use Pusher. And Pusher is really fairly simple. The main thing there is just defining where you want to deploy to. So if you're deploying to serving or light or JS or what have you, that's what Pusher is going to worry about. So Apache Beam, as I've mentioned a few times, is incredibly important in the TFX world. And several of our both our libraries and our components leverage Apache Beam, which I guess is why I'm here. So the Beam vision, you guys know this, but this was a big reason for the choice of Beam as the distributed processing framework for TFX. So this is a compelling vision. The idea that you can run in your language of choice on the execution engine of your choice and still do all of the great things that a distributed processing platform gives you, that's a really powerful thing. This idea of being able to take a beam up and use it on, I mean, you guys know this. I'm really kind of preaching to the choir. Including, although we only use Python currently, including the language interoperability. The portability framework is important to us, especially at this stage of development, because currently most of the runners, as you guys know, run on Java. And it's great that they're there. It's great that all those different platforms are supported, but we're using Python as much of ML does, and having the portability framework gives us the ability to move fairly quickly to other runners. So currently we're using Python Flink and Spark, which use the portability framework. And I think you guys are probably familiar with it, but there's a QR code there if you want to dig in more into the portability API and framework. This is the current, up to, I think, this morning, the compatibility matrix for the 3 different runners that we're looking at. So these are the 3 that TFX currently uses. The Flink runner, the Spark runner, and the Dataflow runner. And again, to emphasize, we're currently only using the batch side of these, but we are interested in the streaming side too. So the call to action for the community. First of all, you guys are pretty aware of this, but there is, we would like to try to see the Spark runner support streaming, so there's a Jira out there available for that. If you have cycles, if you have interest, love to have some love for that. So that's what TFX is. How am I doing on time? I must be okay. So that's TensorFlow Extended. It's really, what we want to do is make available to the open source community, to all of the people out there doing ML, a nice, strong, well thought out framework and platform for doing ML in production. Because ML in production today is not what it should be. And TFX can help, and it's what we use in Google. There's our front page. That's on the TensorFlow side if you hadn't seen it. And thanks.
Thank you so much, Robert. Right on time. I would like to open the floor for questions now. Please raise your hand if you'd like to. Okay, one over there.
Hi, thanks for the talk. Could you give some details on the metadata store you are using, which kind of store and how you are using it to store the metadata? Which technology you are using for the metadata store?
Okay, so you're looking for more details on the metadata store? You want to take that? Sure, why not?
So ML metadata is a set of, it's a library in itself, and it also has pluggable backend storage. So the actual place where we store the information can be SQLite for local development and testing, or also MySQL for kind of long-term testing. But ML metadata offers not only low-level APIs, but over time, higher-level APIs that help you with ML-related CUJs. So think of it as a library that has a pluggable backend. Does that answer your question?
Yeah, thanks.
Okay. Yeah.
Thank you. Next question.
How well is sequential examples or data handled? Does it handle it just as well as tabular data?
I didn't get the last part. Does it handle well what?
As tabular, just normal examples.
Oh, temporal examples?
Yeah.
Right.
No, so not temporal. Tabular. A table.
Oh, tabular.
Table-like.
Yeah. So there's a couple of different levels to that. We currently support TF examples, not TF sequence examples. So if you know the difference between the two, I'm not sure that that's really much of a limiting factor, but maybe it is for particular use cases that I'm not aware of. For sequence examples in general, things like an LSTM or doing text processing or so forth, we support it just like any other TensorFlow thing. There's a lot of support for that kind of thing.
Yeah, so TF example is very mature throughout all the components, TF example support, whereas sequence example support, which is usually how you would encode this kind of data, is actually not on par with that. We do have some plans that will allow us to standardize both our on-disk and in-memory formats, that once that happens, it should allow us to unblock not only sequence example, but arbitrary structures, arbitrary nested structures. So you can think of it as a way to going from an arbitrary nested structured data set to a tensor. And once we have those mappings in place, this will be much easier to support. So we don't want to do it as a one-off. We would rather do it once we have our in-memory and on-disk formats standardized properly. And we're working on some Arrow integration, Apache Arrow integration, to actually help us do that. I don't have exact dates, unfortunately, but look for it. Yeah.
Before I forget, lost it. My Twitter handle was up there. You guys could follow me.
Another question is in the transforms. So the transforms end up being baked into the machine learning model, right?
Yes.
Yeah. So you are also limited to transformations that you can do in TensorFlow.
That is very perceptive.
Okay.
Yes. We can only do things in TensorFlow Transform that we can do in TensorFlow.
Yeah, okay.
So it's not arbitrary.
No, so you wouldn't, for example, I'm thinking things like tokenization, for example. Would tokenization, would you be able to do tokenization?
Well, we can
more
do
advanced than, I know TensorFlow can split on spaces, for example, on white space.
So we can do vocabularies, for example, and embeddings, if that's the kind of tokenization. I mean, actual text tokenization, I'd have to think about that.
Yeah, so I think there's two aspects to your question, and let me clarify a little bit. So you're correct that if you want to do a transformation that has a form of a map, right, and that has to be replayed at serving time, then the way to do it is with something that is portable across your training and your serving system. So that's why you're limited to the portability that we have today, which is TensorFlow. Now, having said that, if you want to do a custom reduction, right? So today, let's say we offer vocabulary construction, or we offer quantiles, or something else. So those are kind of the analysis phase of the transformation. There you actually have the power of Beam at your disposal. So you can write custom analyzers that are fully customized to whatever you want to do. As long as you can transform that into a TensorFlow constant, then it's flexible. Now, on the second part you mentioned, what kind of map transformations do we support? Yes, we're absolutely limited to what TensorFlow can do, but I think you'll be pleasantly surprised because there is a TF-text module that allows you to do text-like manipulations. Splitting is one of them, but there's a lot more. You know, there's segmentation, sentence parsing. As of recently, I think we open sourced some language models that are very strong as well on TF Hub. So I don't know if you're aware of this, but you can actually, in your transform function, you can pull in a TF Hub module and make it part of your transform function, right? So any TF Hub module that exists today on TF Hub, you can actually plug into your transformation system. So you're correct that it's limited by TensorFlow, but it's also as expansive as TensorFlow at the same time. So it's a double-edged sword, yeah.
Yeah, actually, you can pull in models not just from Hub, but also your own trained models could be pulled in that way.
All right, thank you. Unfortunately, we don't have more time for questions, but while we set up the next speaker, I would encourage you to speak to Robert and Gus about TensorFlow, and we'll continue shortly. Thank you.